Hey everyone, in this video we're going to go over section 4.3, how derivatives affect the shape of a graph. Another way of thinking about this, instead of how derivatives affect the shape of a graph, what we're really going to be doing is trying to figure out what information, I'll write this down, what information about the graph of some function f of x. So what information about the graph of f of x can we learn from its derivatives? Really, we're going to use the first derivative of x and the second derivative of x to gain some information about this function f of x, and we're going to use that information to sketch graphs. I'm going to say that verb again, sketch. When I ask you to sketch, that's an approximation. If I wanted something precise, if I wanted something exact, I would teach you guys how to code, and I would have you render these plots on a computer and print them off and give to me. The whole point of this exercise, of this section, is to develop an intuitive understanding of what these functions are doing. Not so you can upload yourself into the matrix and immediately know everything there is to know about them, but so when you're going on to your future classes, you can analyze the functions that are presented to you quickly. You can figure out where they increase, where they decrease, get an idea of where maximum and minimum values are located at. After all, I assume most of you are going on into some flavor of STEM that doesn't start with M after this, so you'll be exposed to a lot of functions and their real-world applications, and you'll probably want to maximize or minimize something. So, like I said, this is just a sketch. This is to help you get more of an intuitive understanding of what's going on. It's like if you asked someone how to get somewhere and they drew you a map. If you wanted something precise, we'd pull it up on Google Maps, but we're going to quickly sketch to gain information about a function. So, let's start off with the first derivative. What does f prime of x say about f of x? Well, remember that f prime of x gives us the slope of f of x at some point. So, what that says is f prime of x, if it's greater than 0, well, this function has a positive slope. F of x has a positive slope. But so it's true that it has a positive slope. The way the words that it gets used is if f prime of x is greater than 0 on some open interval, a to b. So we have a positive derivative over this interval that says, that implies, or then, f of x is increasing on a to b. So we have a positive slope. If something has a positive slope, it's increasing. We read graphs from left to right. So reading from left to right, positive slope means the y value is going up. So if the derivative is positive on this interval, then the values of y's are going up on that interval. The same but opposite is true. So this is our formal statement, and skipping straight to the formal statement. If f prime of x is less than 0 on some open interval a to b, then the opposite is true. F of x is decreasing on a to b. So, for example, if we had f of x being equal to x squared, we can graph this thing. This is straightforward to graph. We go through 0, 0, 1, 1, and 2, 2, 3, 4. Same over there. Oops. That was a horrible plot of x squared. I'm sorry, you guys. Something more like that with arrows on both sides. And now the derivative, f prime of x is equal to 2x, which looks like this. And then we'd go through there. And now, where the derivative is positive, f prime of x is positive, our values of y are going up. Our values of y are increasing. F of x is increasing, meaning the y values are going up as we read this graph left to right. Over here, f prime of x is now negative. F prime of x is negative over here. And what it says is f of x is decreasing. It's positive, but the values of y are going down as our values of x are increasing. So the derivative being negative means that the original is just decreasing. It could be decreasing in positive, it could be decreasing in negative. It doesn't tell you anything about its vertical position, it just tells you about the trend in the values of y. When the derivative is less than 0, the y values are going down. When the derivative is greater than 0, the y values are going up. So let's find, this will be the true example 1. This is example 1 out of the book. We've got this function f of x. It's equal to 3x to the 4th minus 4x cubed minus 12x squared plus 5. And we're going to find where f of x is increasing and find where f of x is decreasing. So find where f of x is increasing slash decreasing. Well, increasing and decreasing, this is all information we get from f prime of x. Increasing is when f prime of x is positive, and decreasing is when f prime of x is negative. So that tells us we need to take f and we need to calculate its derivative. F prime of x is going to be equal to 4 comes down, that's 12x cubed minus 12x squared minus 24x plus 0. If we want to set this thing equal to 0, and I'm going to pull out a 12x from each of these terms, we'll get 12x times x squared minus x minus 2 is equal to 0. We can factor this. That'll turn into a 12x times an x minus a 2 times an x plus a 1, and set that equal to 0. So the reason why we're setting these things equal to 0 is because the sign is going to change on either side. So what do I mean by that? I mean that we know the derivative equals 0 when x is equal to 0, or x is equal to 2, or x is equal to negative 1. So to figure out where we're increasing and decreasing, we're going to make a sign chart. I'm going to put 12x, I'm going to put x minus 2, and I'm going to put x plus 1, and I'm going to put their entire product. Now, instead of writing 12x times x minus 2 times x plus 1, because that's going to take up this much space right here, this thing is the derivative. So I'm just going to call it f prime of x. So we're making a table. And so now, what points are we going to put on our table? We need test regions. So points we care about are here at negative 1, over here at 0, and over here at 2. So we have 4 regions. We have this region over here, we have this region over here, we have this region right here, and we have that region right there. What we want to do is we want to pick any value. These are just values of x. So we want to pick any value of x that's less than -1, and we want to plug it back into our derivative. I am going to pick at random -2 for a test point. Oops. I should at least try and make my t's taller than my e's. So this is a random. It's not really random. We were guided that it has to be less than -1, but it's effectively a random point. I could have chose -2.5, could have chose -3, I could have chose -100 or -17. I just had to pick a number less than -1. Okay, so -2. 12 times -2 is -24. All I care about is the sign. On any interval, for any number less than -1, 12 times that number is going to be a negative number. -2 take away -4 is also a negative number, and -2 plus 1 is also a negative number. So what we're doing is we're evaluating the sign of each of these factors. Now what we're going to do, f prime of x is the product of all these factors. A negative times a negative times a negative is a negative. And what that tells us is we are decreasing on this interval. Now, we pick any number between -1 and 0. You can't pick the endpoints, you can pick any number in between. -1/2 is in the middle. So I'm going to pick that as our test point. Now we go through. -1/2 times 12 is -6. We care that it's negative. -1/2 take away 2 is -2.5, -5/2. It's still negative. But -1/2 plus 1 is back to being a positive number. Now we go through a negative number times a negative number times a positive number. Well, negative times negative is positive, and positive times positive is positive. Our derivative is positive on this interval, or we are increasing on this interval. Now we pick any number between 0 and 2. I'm going to pick 1 because it's easy. 12 times 1 is a positive number, 1 take away 2 is a negative number, and 1 plus 1 is a positive number. Positive times negative is negative, negative times positive is negative, so we are decreasing, and I'm sorry, I wanted to put my plus up here, and I would put a minus sign down here. Kind of wrote it in the middle. So we are decreasing. And finally, we pick any number bigger than 2. I'm going to pick 4. 12 times 4 is a positive number. 4 take away 2 is a positive number. 4 plus 1 is a positive number. And positive times positive times positive is positive, or we are increasing. So the final subtlety is that you can only increase on an open interval. It can be argued that where you have a critical point, your function is neither increasing nor decreasing, but you're certainly increasing up to this point and away from that point. So, when you're asked find where f of x is increasing, the way I write my answer is I write increasing. I always write INC because I'm horrible at spelling. I increase from -1 to 0, and we always put parentheses. We're also going to increase from 2 out to positive infinity. And we need to tell the reader that the combination of these intervals are our answer, so we need a union sign. You have to use your union in between your intervals. Okay, where are we decreasing? Well, we're going to decrease from -infinity out to -1, and we're going to also decrease from 0 out to 2. So this is the takeaway. We're taking our function, we're taking its derivative, And then we're breaking up the derivative as best as possible. Usually factoring is what you're going to do to get to this step. Then you make a sign chart. Each of your factors, 12x, x minus 2, x plus 1, goes in a column, along with f prime of x. This is the thing we really care about. Getting information about this thing is why we're doing all of this. So don't forget an f prime of x here. And then you pick any value in between where your derivative equals 0. So our derivative equals 0 at -1. So I had to pick some value less than -1. I chose at random -2. Like I said, I could have chose at random -17. I recommend you choose a number that's easy to work with. But I'm not here to tell you what to do. You're free to pick any number that makes your heart happy. Just make sure it's smaller than -1. Then pick any number between -1 and 0 that makes your heart happy. 0 and 2, and 2 and infinity. You're testing each of these regions, figuring out the sign of the parts, and using the sign of the parts to figure out the sign of the whole. Where your derivative is less than 0, you're decreasing. Where your derivative is greater than 0, you're increasing. So continuing on, example 2 is just a continuation of example 1. So for example 2, we want to find the local maximum and minimum values of x. Of f of x, I should say. And for example 2, we're going to use that same example, or that same function in example 1. That was a 3x to the 4th minus 4x cubed minus 12x squared plus 5. So if we want to find the local and maximum values of f, we know that the local maximum and minimum values are going to occur at the critical numbers. We want to figure out where f prime of x is equal to 0. And we've already done that. We did that back here, and we know that that means that x is equal to 0, or x is equal to 2, or x is equal to -1. It's important that you write the word or. If you don't write the word or, you could be saying that x is equal to 0 and x is equal to 2 and x is equal to -1, but that doesn't work. That's saying 0, 2, and -1 are all equal to each other. You need the word or, because x can take on different values here. So we want to find our local maximum and local minimums. That means we want to figure out the value of f given these values of x. So we want to calculate f of 0. F of 0 is straightforward. That's 0 to the 4th minus 0 cubed minus 0 squared plus 5. F of 2 will require a little bit more work. It's equal to 3 times 2 to the 4th minus 4 times 2 cubed minus 12 times 2 squared plus 5. 2, 4, 8, 16. And 16 times 3 is 48. 2, 4, 8. 8 times 4 is 32. Minus 4 times 12 is 48 plus 5. Oh, we've got a 48 and a negative 48, and that's equal to negative 32 plus 5, which is negative 30 plus 3, which is negative 27. And finally, we need to figure out f of -1. F of -1 is equal to 3 times -1 to the 4th minus 4 times -1 cubed minus 12 times -1 squared plus 5, which is 3 plus 4 minus 12 plus 5. Oh gosh, that's 9, 10, 11, 12, which is equal to 0. Perfect. So we have, and yeah, all those are right. So our local max is going to be at the largest y value right here. Our local max. Our local min is at our most negative number, our largest number in the negative direction. Like I said, I have mixed feelings about calling this the smallest because 0 is definitely smaller than negative 27, but that's the most negative for sure. Local maxes are at our biggest number, regardless of what it is. And local minimums are at the most negative number, the biggest in the most negative direction. So moving on to example 3, we're going to do just another example of finding local maximum and local minimum values. We're going to find local max and min values of f of x is equal to x plus the sine of x plus 2 sine of x over 0 to 2 pi. Perfect. So first off, local max and minimums. Local is not the endpoints. Local is not endpoints. You have to have an open interval to find a local maximum, so we're not going to test at 0 or at 2 pi. We're just looking somewhere in this interval where the biggest values are. Well, the local maximum and local minimum values, they are going to occur where either the derivative doesn't exist, we've got to find our critical values of x, or where the derivative is equal to 0. Regardless, we need that derivative. F prime of x is equal to 1 plus 2 times the cosine of x. Cosine of x is defined everywhere, and you can always add 1 to a real number, so we're good. That derivative exists everywhere. Well, that means we need to figure out where that derivative is equal to 0. So mystical algebra says that we want to figure out where the cosine of x is equal to negative 1/2. I personally always draw a picture when I do my inverse trig stuff. The x value is negative 1/2 up here and down here. So this is going to be at 2 pi thirds and at 4 pi thirds. That tells us x equals 2 pi thirds or x equals 4 pi thirds. Put that over there. And we have a backside. So I'm just going to write f of x is equal to x plus 2 sine of x. So we want to figure out which one the local max and which one the local min is. So we want to figure out what f of 2 pi thirds is. And that's going to be 2 pi thirds plus 2 times the sine of 2 pi thirds, which is equal to 2 pi thirds plus 2 times the square root of 3 divided by 2, which is, these will cancel out. 2 pi thirds plus the square root of 3, and I feel very strongly that I should call this 2 pi plus 3 times the square root of 3, all divided by 3. You can definitely stop at that step. I am compelled by some force of nature to carry it to that step. The next thing we do is we want to figure out what f of 4 pi thirds is. And that's going to be equal to 4 pi thirds plus 2 times the sine of 4 pi thirds, which is 4 pi thirds plus 2 times a negative root 3 on 2, which is equal to 4 pi thirds minus root 3, because these 2's will cancel, and once again by that same force of nature, 4 pi minus 3 root 3 all divided by 3. At this point, you would just plug these into a calculator, and let me get you their y values out. I will be right back. So, plugging these into calculators, 2 pi plus 3 root 3 all on 3 is about 3.8, and 4 pi minus 3 root 3 all on 3 is about 2.5. So over the interval of 0 to 2 pi, we have a local max at x is equal to 2 pi thirds, and a local maximum value of f of x being about 3.8, being about 3.8. So we've got a local max at this value, and the local maximum value of f of x is that number. We also have a local min at x equals 4 pi thirds, and a local minimum value of f of x being about, and a local minimum value of f of x being about 2.5. Perfect. So we have these extreme values. Our extreme values are going to occur where the derivative is equal to 0, which the picture should make sense, because we're going to increase to a point and then we're going to decrease from it. If you increase to a point and then decrease from it, that means that point that you started to decrease from was higher than where you were at. You increased to a point, your direction changed, your derivative was equal to 0, and then you decreased. So we're finding critical numbers, and where those critical numbers occur, we might have a local maximum or a local minimum. We have to test all of them to know which one is which. Alright, so this next example, example 6, if I remember correctly. Example 6. Yeah. Example 6, what we're going to do is we're going to sketch f of x is equal to x cubed, x to the 4th minus 4x cubed. X to the 4th minus 4x cubed. So in order to sketch this function, we're going to get some information from the function itself, we're going to get some information from its derivative, and we're going to get some information from its second derivative. We're going to fill probably this whole sheet with information, and then on the back side we're going to sketch it. So what can we learn, what do we get from f of x? From f of x, we get our roots. By that, I mean we figure out where this thing crosses the x-axis. In order to figure out where f of x gets our roots, well, that means we want to know where f of x is equal to 0 at. Well, x to the 4th, and we want 0 to equal x to the 4th minus 4x cubed. Well, that's the same as I can factor out an x cubed times x minus 4, and that tells us x is equal to 0 or x is equal to 4. So this gives us 2 points on our graph. We know our graph is going to contain the point 0, 0, and it's going to contain the point 4, 0. This is all we're really going to use our original for, aside from getting some more y values out. Largely, our original gets y values, but we can also figure out our roots. From our first derivative, well, that's going to be equal to 4x cubed minus 12x squared. In order to find our critical numbers, we need to set our derivative equal to 0. When 0 is equal to 4x cubed minus 12x squared, which is the same as 4x squared times x minus 3. That right there tells us that x is equal to 0 or x is equal to 3 for our critical numbers, where we have a horizontal tangent line. And so we can go back to our original to figure out their y values. F of 0 is equal to 0, and f of 3 by magic is actually going to be equal to negative 27. So we know at the point 0, 0, we have a horizontal tangent line, and at the point 3, negative 27, we have a horizontal tangent line. We don't know if we have a maximum or minimum there yet. You can kind of look and see which one's going to be our minimum. Let's go on and work with the second derivative. F double prime of x is going to be equal to, and I'm going to look right here, 12x squared minus 24x. If we want to find our inflection points, that means we want to know where 0 is equal to 12x squared minus 24x, which is the same as 12x times x minus 2. That information right there tells us that we have an inflection point when x is equal to 0 or x is equal to 2. Well, we plug these back into our original. F of 0 is equal to 0, and f of 2 is going to be equal to negative 16. So at the point 0, 0, we have an inflection point, and at the point 2, negative 16, we have an inflection point. So we know where our critical points are, and we know where our inflection points are. Now we can double back. Now, let's figure out where we're increasing and decreasing on. So we're going to increase. So looking at our derivative, we're going to break it up like we did. We're going to have a 4x squared. We're going to have an x minus 3. And we're going to have a f prime of x. This is increasing slash decreasing. We're going to figure out all that information. Leave some space. So the points we care about are x is equal to 0 and x is equal to 3. So we'll put a 0, we'll put a 3. We can pick any number from this region. I'm going to pick negative 1. Negative 1 squared is 1 times 4 is a positive number. Negative 1 take away 3 is a negative number, and positive times negative is negative. I'm going to pick up positive 1. 1 squared is 1 times 4 is a positive number. 1 take away 3 is a negative number, and positive times negative is a negative number. We can pick any number bigger than 3. I'm going to pick 5. 5 squared times 4 is a positive number. 5 take away 3 is a positive number, and positive times positive is positive. What this tells us is we're actually going to decrease on negative infinity to negative 1 union, to 0, 0, union with 0 to 3, and we're going to increase on 3 to infinity. We can also figure out where we're concave up, or down. We look at our second derivative. We're going to have a 12x. We're going to have a x minus 2. And now we're going to have the second derivative of x. The points we care about are when x is equal to 0 and x is equal to 2. And we want to test numbers that aren't these numbers. We can pick, say, negative 1. Negative 1 times 12 is a negative number. Negative 1 take away 2 is a negative number, and negative times negative is positive. I can pick any number in here. I'm going to pick 1. 12 times 1 is a positive number. 1 take away 2 is a negative number. Positive times negative is a negative number. And finally, something over here, I'll pick 3. 3 times 12 is positive. 3 take away 2 is positive. Positive times positive is positive. So what this tells us is that we are concave up from negative infinity out to 0, union with 2 to infinity, and we're concave down on 0 to 2. Okay, so there's a lot of information going on over here. We took our original and we got our roots. We took our first derivative, we got our critical points. We took our second derivative, we got our inflection points. We used our first derivative to figure out where we increase and decrease. We use our second derivative to figure out where we're concave up and concave down. Now, what we can do is we can actually use, we can use the second derivative test. I kept on looking at the wrong spot. What our second derivative test says is, so we know we have this critical point when x is equal to 3. Well, when x is equal to 3, we're concave up. So, we know this is going to be a local min. We know it's going to be a local min from the second derivative test. We're horizontal and we're concave up around it. So it has to be on the bottom half of that parabola. And I don't want to say that parabola, that portion is kind of parabolic in shape. As compared to over here, if you look, well, we have a horizontal tangent line, but our function is neither, our second derivative is neither positive nor negative at that point. Don't look too far into, and I have lost it, don't look too far into the second derivative test. What the second derivative test says is if you have a horizontal tangent line and concave up, it tells you some information. Or if you have a horizontal tangent line and concave down, it gives you information. It doesn't give you any information about what happens if you have a horizontal tangent line and you're neither a concave up or a concave down. We don't know anything about this from the second derivative test. But from what we have here, we can come up with a pretty good sketch of what this thing looks like. So let's put all this information into a sketch. This thing's going to get fairly tall. We'll do this. We'll try and connect the dots. You do not need to draw your graphs to scale. You just need a sketch. I'm going to try and draw this thing to scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I might be able to do it. 1, 2, 3, 4, 5, 6, 7. There we go. We need to go all the way down here. And this is negative 27. This is negative 10. This is negative 20. Perfect. I've got this point 3, negative 7 I'm trying to fit on here. So working top down, we know we have these roots. We know we're going to cross the x-axis when x is equal to 0 and when x is equal to 4. 1, 2, 3, 4. Okay, we also know we have a horizontal tangent line, or the slope of this function is 0 at the point 0, 0, and it's 0 at the point 3, negative 27. Okay, so we have our horizontal tangent lines. We know we have an inflection point at 0, 0, and we have an inflection point at 2, negative 16, 19, 18, 17, 16. So there's 2, negative 16. Now we have this information about decreasing and increasing. So we know we're decreasing from negative infinity to 0. We don't know any of the values of this function between negative infinity and 0. All we know is that we're decreasing. There's a handy-dandy rule that gives you values of y given a value of x, but we're not trying to calculate every value for this function. We know we're decreasing, so it could look something like this. We know we're decreasing, and we have to belly out and go flat through here. We also know we're going from concave up, and at this point we're going to start to go concave down. We still have a horizontal tangent point, or tangent line, and we're still concave down. But at this point, we're actually starting to belly up. We're trying to pull out of our nosedive. That's no longer a function. Trying to pull out of our nosedive, and we do it, and then we go concave up. Well, we went concave up over here. And then, so from 0 to 2, we're concave down. Now we're concave up from 2 all the way out to infinity. So we stay, and this is going to get really steep, and we're going to stay concave up for the rest of infinity. So let's talk about this. We have a 0, we have a root at 0, 0, and a root at 0, 4. We have a horizontal tangent line at 0, 0, and we have a horizontal tangent line at 3, negative 27. We can look and see that this is a local minimum, but also using our second derivative test, we knew this was a local minimum. We had an inflection point. We went from concave up to concave down right here at 0. And at the point 0, 0, I'm sorry, and we had another inflection point right here at the point 216. It's hard to tell from the sketch, but we're going from concave down, we're opening downward, and at this point we go the other direction. We start to open up, and we're going to be concave up from 2 for all values of x from 2 all the way out to positive infinity. The way I drew it here, the way it went off like this looks like it's concave down. So I need to keep my line more straight to show that it has to be concave up. Sorry, that part of the sketch looked misleading. Concave up. It's really hard to draw a straight line from negative 27 all the way up here. Probably should have stretched this thing out. But we're still decreasing negative infinity to 0. And then from 3 down to, from 0 to 3, we're not decreasing from negative infinity to 3 though. Because right here, we're neither increasing nor decreasing. We have a horizontal tangent line. That's why we have that union in the middle. And then concave up, concave down. There's a lot to these problems. What I recommend you doing is when you start these problems, start with f of x and ask yourself, what information can we get about this function just from f of x? We're not trying to graph it. We're trying to sketch it. So you could say, what information did I get from f of x? All of it. But what information is easily available to you? Well, I can set that thing equal to 0 and find my roots. Okay. F of x also gives us our rules for getting values of y. Then you move on to your first derivative. You take your first derivative, set it equal to 0, find where your horizontal tangent lines are. I don't care if you do your increasing at that step. If I could go back in time, I probably would have done my increasing at that step. You then move on to your second derivative, set it equal to 0, find your inflection points, and figure out where your concave up and concave down. Once you have all of this information, and I admit this is going to be, at least for me, was an overwhelming amount of information, you do your best with the graph. Try sketching it. And I would recommend you guys all go online and you plug this thing into your favorite online graphing thing or on your calculator of choice. By now you know that I will shamelessly use Desmos for everything I can. I'd plug that thing into Desmos to make sure that at least looks kind of like that. But this is the idea for sketching. You take something small, you generate an overwhelming amount of information from it, and then you do your best to graph it. It is do your best. Like I said, I would teach you how to code in Python or something like that if I wanted an exact plot. Hey guys, sorry for the abrupt end. The battery on my camera is dying. But that's largely what we're going to be doing for curve sketching. We find our zeros, we find our critical points, and we find our inflection points. And we're using that information to the best of our ability to come up with just a sketch of a function. Like I said, it's not supposed to be a precise graph. It's supposed to help you guys get a mental image of the way the function behaves as the value of x changes. It's all trying to get you guys used to looking at more of a big picture, kind of a big picture approach to the way functions behave. So for homework, go off and do 1, 25, 29, and 37 through 47. That'll be due this Friday. Take it easy, you guys. Bye-bye.